reminder to switch off your laptops and phones. So we will continue from where the guest lecture left off. It was on remote procedure call, so I'm going to go on from there on. But before I do, I wanted to also remind everyone there is a makeup class scheduled this Friday, because we had another makeup class that I had to cancel on account of illness. So I will have a makeup class this Friday, same room, same time. It will start at 9, not 9:05, and will go on for about an hour, 5 minutes or so. There's another class here right afterwards, so we have to leave on time. Okay? So do come if you can, otherwise we'll make the video available. Okay. So just a recap of what was discussed last time. So we started a new topic which was distributed communication. Okay, and we reviewed this notion of remote procedure calls, or RPCs. Okay. So the basic concept of RPCs is that it makes distributed computation look like local computation. So the basic idea is you don't, as a programmer, you don't need to know a whole lot about networking or write a lot of networking code. You simply structure your program into functions and procedures, okay, and you call functions. Okay, and in some cases, these functions or procedures just happen to be remote procedures. The code for those functions just lives on a different machine in a different process. Okay, so invocation of such procedures is called invoking remote procedure calls, okay, RPCs, and it involves sending a message from the sending process to the receiving process, of the client process to the server process. The function gets executed at the remote process, and the results are returned back to you. Okay? So from a code perspective, it looks exactly like you're calling local functions, except that these are special functions where the code is not part of this process as you normally expect. It's part of a different process. Okay? So that's the notion of RPCs. I presume some of these issues were discussed, which is parameter passing, the fact that you cannot pass pointers to RPCs. Okay, that's not allowed, because when you dereference the pointer on a different machine, it is actually referring to an address, memory address on the sending machine. So that address on the receiving machine does not make any sense. So you cannot pass pointers as parameters, so you pass all arguments by value. Okay, you have to do binding, which is when you start up the server process, it registers itself with a name service. When the client process starts up, it actually looks up the name service to figure out where the server process is running. Okay, so, and I'll talk more about binding today as well. And then the last point was how to handle failures if the client of the server fails. Okay, so I'm going to take a minute to see if there were any questions from last time that I should answer about RPCs. I presume most of you will use some form of RPCs or RMIs for your lab. So it's important that you understand these concepts and use it. You can of course program at a socket level, which I'm also going to cover today, but it may be more useful to think about programming at a higher level of abstraction. Any questions from last time? Okay, so let me continue from last time. So what I'll do today is talk about lightweight RPCs, other forms of RPCs, okay, which are slightly different from traditional RPCs. And then I'm going to talk about RPCs in the world of object-oriented languages, which is essentially remote method invocation. Okay, and I'll talk about that in the context of Java. So let me first talk a little bit about lightweight RPCs. Okay, so lightweight RPCs are a special case of remote procedure call, where the calling process and the called process both reside on the same machine. Okay, they are still independent processes. They just happen to be on the same machine. Okay, normally when the calling process invokes an RPC, okay, the RPC code goes to the stub code. The stub code constructs a message, sends it off to the other process, okay, which is on a different machine. It arrives at the other process, the OS processes it, it's received by the called process, and you invoke the procedure. Okay. Now if the called process and the calling process are on the same machine, you can perform some special optimization that would normally not be available to you. Okay. And if you use these optimizations, you get what are called lightweight RPCs, okay, rather than traditional RPCs. So essentially, it's a way by which you can reduce the overhead. Okay, you can of course use traditional RPCs even when both of those processes reside on the same machine. Okay, you can use exactly the same method, except that what is going to happen is the packets are not going to go over a network. They'll go down the protocol stack and come back up because the called process is actually on the same machine. So there's no need to send any message out. The message just goes to the OS and comes back to the call process. Okay? So you are using message passing essentially as a paradigm for remote procedure calls. Okay, and instead, if both the processes are on the same machine, you can essentially use shared memory as well. Okay? So rather than using explicit message passing using protocol stack, you use implicit message passing using a shared buffer. Okay? You can always send a message by putting some data into a buffer and have another process pick it up. Okay? That's also a form of message passing. It's just implicit, not explicit. Okay, so in lightweight RPCs, what is going to happen is rather than constructing a message, the OS will figure out that the called process actually resides on the same machine. So rather than explicitly constructing a message, it's going to put all the arguments, okay, into a shared buffer, okay, and have the called process take those arguments. Okay, the whole purpose of message passing was to tell the called process which procedure is being called and what are the arguments to that procedure. Okay, here we are going to just put that information into a shared memory region and have the called process pick it up from the shared memory region. Okay? And in doing so, you have saved the overhead of sending a message, because reading and writing to memory is far cheaper than actually constructing and sending messages. Okay? So that optimization is going to give us some performance gains. Okay? And that's essentially the purpose of lightweight RPCs. There are special mechanism where you are going to essentially use shared memory rather than message passing for invoking the RPC. So essentially what is going to happen is the process will be slightly different from before. Okay, you will essentially go to your stub code. The stub code is going to push the arguments onto a stack, okay, which could be the traditional stack or a shared memory region depending on the implementation. You are going to trap into the kernel. Okay, the kernel is essentially going to provide access to this memory region to the called process. Okay? Because you put the arguments onto a memory region, whether it's a stack or a shared memory region, you have to make that available to the called process. So you are going to do something to enable that. Typically that involves changing the memory mappings, okay? But there are other ways to do that as well. Okay, and then the client thread is going to essentially execute the procedure using an opcall in the call process, and then once you are done, you are going to trap back to the kernel and come back. Okay, I have a picture to show this whole thing happening. So here is one machine. Okay, there are two processes, the client and the server. They just happen to run on the same machine. Okay? So normally when you call RPC, it would go down the protocol stack. You will construct an explicit TCP/IP socket message. It is going to come back here. The whole protocol processing is going to be done in reverse, and you're going to go to the server process, which will impose quite a bit of overhead. So what you will instead do is you will take the arguments of the call process, you're going to put it into a memory region, which is not shown in this picture. You're going to put it into a memory region and just tell the server process, go pick it up from there. I'm not going to explicitly send a message. Okay? Now in the context of Solaris, which is a Unix-like operating system, which supports lightweight RPCs, this mechanism of a lightweight RPC is called a door. Okay, that's just the term that is used there. It's essentially the same concept. Okay, and what is actually shown here is a door call, which is essentially going to do all of what I just talked about. So you have to have a server process, register the RPCs with the OS or a naming service, and when the client process calls it, it's going to essentially pick up the arguments from a memory region. Okay. The other interesting thing is, in case of Solaris, you can actually use a runtime flag to tell the OS whether to use a traditional RPC or a lightweight RPC. If the called process and the calling process are both on the same machine, you can just use a runtime argument to tell the OS that this is a special case, use a lightweight RPC mechanism instead of a traditional RPC. So it will just use the same procedures but use a LRPC mechanism to pass arguments rather than explicit message passing. Okay, is that clear? Any questions on lightweight RPCs? Okay, so they're just a special case of RPC is optimized for the scenario where the client and the server run on the same machine. Now here are some other RPC models. Before I talk about RMIs, I'll introduce a few other RPC mechanisms. So the traditional RPC mechanisms uses what is called synchronous RPCs, okay, or blocking calls. Okay, synchronous essentially always means blocking. Okay. So when you make an RPC call, the calling process is going to block, okay, wait for the function to execute and return results back to it. So until all of that happens, the thread or the process that called the RPC is going to just block. Okay. This is called synchronous. Okay. Essentially, they're all blocking calls. That's how normally when you call a function, that function has to wait until the called function returns. Okay. So it's always blocking. Now, not all RPCs have to be synchronous or blocking. There are RPC modes that will use other mechanisms. Okay. So I'll introduce three: asynchronous RPCs, which is a non-blocking version of RPC. There's a deferred synchronous RPC, which uses two asynchronous RPCs in both directions. And then there is something called one-way RPC. Okay, let me introduce the first two, then we can talk about the third. Okay, so here's a picture that illustrates the difference between synchronous and asynchronous. Okay, so the left picture is a traditional RPC mechanism, which is synchronous or blocking. Okay, this is timeline on the x-axis. The top line is the client timeline. The bottom line is the server timeline. The dark line indicates that the process is executing. Dotted line indicates that you are waiting. Okay, so you'll see that the client is executing, and the client makes an RPC request, and it blocks. The RPC request is sent over a network as a network message to the server. The server executes the process or procedure rather. It makes a reply message, sends it back, and then the client is blocked waiting for that RPC to execute throughout that period. And then once the return results come, it continues execution. Okay, so that's blocking or synchronous. In asynchronous RPCs, you are not going to wait for the return result. You are simply going to send make an RPC call, okay, and then continue execution. Okay. Now in this case, you made a call at this point, okay, and then you are just waiting for an acknowledgement saying the RPC call was received by the server. Okay. Once you get an acknowledgement saying the RPC was received by the server, you don't wait for the RPC to actually execute and return the results to you, you just continue execution. Okay. So this is a non-blocking version of the same RPC mechanism. Okay, the return results will come back to you at a later time, okay, but you are not blocked waiting for the return results to come. Okay. When I talked about event processing system or asynchronous servers, I mentioned asynchronous calls. Okay, if you remember asynchronous I/O and so on. Here's an example of an asynchronous call that does not block, okay, waiting for the RPC to complete. Is that clear? Okay. So deferred synchronous RPCs essentially uses two one-way RPCs or two asynchronous RPCs where the results are returned in the reverse direction through another asynchronous RPC. Okay, so here's your client. Client makes an RPC request. Request comes to the server. Server sends an acknowledgement. Client continues executing something else. Okay, and then in the meantime, the server is going to take that RPC request, execute it. At some point, a return result is produced. And the return result is sent back to the server as a reverse one-way asynchronous RPC. Okay, so you essentially return the results, which will come back to the client. The client will then get interrupted and get those results, and then you send an acknowledgement. Okay, so this is called deferred synchronous RPCs. Okay, is that clear? Okay. Yes, question.
Since the response is via an additional async RPC, so how is the response in a single async RPC?
Okay. So
is it going to be the same thing? Then
question is, how is the response in a single, what is happening to the response here? Okay. So there are one of two things you can say. One is that I may not need a response. I'm just sending some information to the client server and let the server deal with it. But if you do need a response, either you have to use the deferred version, or you have to essentially have a callback mechanism or a notification mechanism. Okay? So the results will come back, and the client's stub will then interrupt you through a notification saying your response is error. That is not shown in the picture here. So if you had a notification at some later point, a message will come back with the return results, and you will get interrupted. Okay? So in this case, the return results are coming from through the RPC mechanism itself rather than a interrupt or a notification. Okay?
So for the second part on notification, so is there any callback interface built into RPCs just for listening for something without keeping ports open?
So the question is there a callback interface for asynchronous RPCs to return the results? Okay? If you have a RPC system that supports asynchronous RPCs, it will have a callback interface. In fact, next class, we are going to look at message queuing systems that actually support asynchronous versions of RPCs. And we will see that it does actually support callbacks of this fashion. Okay, so you will indeed need a callback mechanism. Traditional RPCs may not even support this. Okay, you may just have the default synchronous RPCs. In that case, you cannot do any of this. But there will be RPC systems that do support asynchronous calls as well. Okay. Any questions here? Okay. So the final one, which I don't have a picture for, but which is on the slide here, is one-way RPCs. In one-way RPCs, that you are essentially making a call. It is asynchronous. You send a RPC call to the server, but the server is not even waiting for an acknowledgement from saying that you received the request. Okay, in this case, okay, you are essentially receiving an acknowledgement. Until then, you are blocked. Okay, you are at least blocked so that you know that the message was received by the server and the server is going to process it. Okay, in one-way RPCs, this arrow is gone. You simply send a request and then you continue execution. Okay, and then you don't even see whether the server has received it and whether it's executing. Okay, so that's one-way RPC. So in this case, reliability is not guaranteed because the client does not know that the RPC request was even received by the server. Okay? But if you are running on a reliable network, it will reduce the overheads even more, where it is truly non-blocking. Once you send the message, there is no blocking at all. In this case, there's a limited amount of blocking, at least waiting for an acknowledgement to come back. Okay, so in one-way RPCs, you don't even have that. You just send a request and you're done. Okay? So that's one-way RPC. So these are three different models that differ from the traditional synchronous blocking mechanism. They are used in advanced RPC systems where you're trying to get extra performance. Okay, because the normal method is the easy one to program, okay, and it is easy to understand. Some of these are more complicated because you might be executing something else. A callback occurs, you have to switch back to the RPC you send, process the result, and then switch back to whatever was happening. So it complicates application programming, okay, but gives you more performance because you are not blocking involved. Okay, so I'm going to move on and talk about RMIs for the rest of this class, or remote method invocation. Okay. RMIs are essentially RPCs in the object-oriented world. Okay, so if you use Java or use other object-oriented languages, RPCs are essentially supported as method invocations on objects. Okay, except that these objects now will reside on other machines, not in the same process. In a traditional Java process that you write, you will have a Java class, you will instantiate an object, the object will support a bunch of methods. Okay, you can just call object.methodName, okay, and then it will just invoke the method on that object. In RMIs, this object will now not reside in this process, it will reside in some other process on other machines. So you can still call object.methodName, okay, except that now your runtime system will realize that this object resides somewhere else. So you'll actually construct a message that will be sent to this other process saying invoke this method on this object, which is a remote object. Okay, so then you'll execute the object method and then return the results. Okay, so exactly the same RPC mechanism, but viewed in an object-oriented mode. Okay, so you'll have the same kind of concept. There will be classes that essentially have code for the objects, because they're object-oriented abstractions. You will have the same separation of interface from implementation. Okay, the interface will reside on the calling machine. The calling machine will know that this object has these kinds of methods. That's the interface for that object. So you can call those methods. Okay? The implementation of those methods will be on a different machine in the context of where the object actually resides. Okay? So let me show you a picture. I don't know whether I have a picture here. Let me show you. Oh, we do have a picture. Yes. So here is an example of what's going on. So this is the server machine, that's the client machine. Okay? So you return some code in that gray box, okay, that has the state of the object and the code for all the methods of the object. Okay, let's call it object foo. Now on the client machine, okay, you can actually call methods on the object. So you can call foo.method1. Okay, just as you call a normal method on a Java object. So what will happen in that case is the RMI call, which is a remote method invocation call, will come to the stub code. The stub will realize that this is a remote object, not a local object. It will construct a TCP/IP message. That message will be sent over the network to the server machine. It will arrive at the server stub. The server stub will unpack that message and call the method on that object locally. Okay, now that you have it here, you can just call that method foo, method1 on that object. That method will execute. It will provide, generate some return results, which will then be sent back to the client, and then the client will essentially be handed back those return results and continue execution. Okay, so that's how RPCs work as well, except that now we have extended this notion to calling methods on objects. Okay, in this case, the objects are remote. Okay, so you'll call this distributed objects rather than local objects. Okay, so now when you write your code, object-oriented code, you have to always decide whether something is local or remote. Okay, you will basically partition it into, this one shows 2 processes, but you don't have to have 2. You can have n processes. Okay, so each process can invoke methods on objects that are present in other processes. So they will all be handled using RMI calls. Okay, like before, the programmer does not have to deal with all of this part where you constructed a message, sent it over. That's taken care of for you automatically by the runtime system. All you're doing is calling foo.method1 as if it's a local object. Okay. The part where you have to set up a connection to the server, construct a message, send that message over, unpack it, all of that is handled automatically. That's the entire power of RPCs and RMIs, where you do not do low-level network programming. That's handled by the runtime system for you. Unlike if you're programmed at a raw socket level, you have to deal with, in your application code, deal with constructing a connection, creating a socket, constructing a message, sending it over the socket, and so on. All that is automatically taken care of by the stub code. Okay, so that's the concept of RMIs. So in this case, and this is the picture shown for Java, you still have stub code, except that the stub code is called the proxy code at the client and the skeleton code at the server. Okay, but it's essentially the same thing as RPC stubs, the client stub and the server stub that you saw last time. Okay, so they're just different terms, but the concept is exactly the same thing. Okay, now, again, like in RPCs, the stub code takes care of a whole set of things for you, so you don't have to write code for it. Okay, first, it's basically going to, the server stub is going to register itself with a naming service, so that the client can figure out which port the server is listening on. Okay. It will set up the connection with the server and tear it down. You don't have to write code to do TCP/IP connection. You can also do marshalling and unmarshalling of arguments using the stub code. Okay, so you can package arguments using in Java, this is called serialization. Okay, in C or C++, this is called marshalling and demarshalling of arguments. Okay, as you may have seen last time, whenever you pass arguments that are more complex data structures, you have to essentially construct a byte stream for the object. Okay, so and then you have to send it over and you have to reconstruct the passed argument at the other end. Okay, this also takes care of things like architectural differences. Okay, because the client may be on big Indian architecture and the server may be on little Indian architecture. In big Indian architecture, the bits are read from left to right and the little Indian is left to right. If you just send an integer, which is a set of bits, if you interpret it the wrong way at the other end, then you are going to essentially not get the right arguments. Okay, so when you do RPC calls, you have to deal with architectural differences. That is handled by marshalling and demarshalling of argument. You always convert everything into an external data representation, which is a known format. Okay, and then you retranslate it from the external data representation to your native architectural representation. Okay? The same has to be done here, because there's no assumption that the client and the server are the same architectures. Okay? They may not even be running the same OS. Okay? So long as you can support remote objects, the platform does not have to be the same. So you have to deal with platform differences using stub code and doing serialization and desynchronization. Okay? So all of that is actually handled for you. The good news is you don't have to worry about it. Okay? The stub code will deal with it. Okay? But you need to know that that's happening underneath, okay? So that you understand, get some appreciation of what's actually being done. Okay? So that's all happening in the client stuff, and the server stuff is just going to listen for messages. When our RMI call arises, it's going to extract the argument using deserialization, pass the parameters to the called object and the method, wait for the results and do the reverse. Okay? Send the message back. Okay? Now here is some snippet code that shows how a client can bind to a remote object. Okay? So there are two ways of doing binding. One is explicit, the other is implicit. Okay? In both cases, the server code, when it starts up, registers itself with some naming service. Okay? So what you have done is saying, I am server with this name, foo. Okay, I have this methods that I am these objects that are exposing remote method, and you register yourself. You also register which port number you are listening on. Okay? So you don't need to hard code anything. When the client runs, it has to first locate the server. Okay? Because from a programmer's perspective, all you called is foo.method1. You did not even say which server is it running on. So it's up to the client code, stub code, to figure out where the server runs. And the way you're going to do this is you're going to bind yourself to a server by looking up the server in the naming service. Okay. And whether you do this explicitly or implicitly, the stub code again takes care of this for you. So in the first case, all you have essentially done is you just called object.method. Okay, this is C++, but so you have arrow there rather than dot, but the same thing applies in C or Java as well. So when you first call a method on a remote object, then the stub code will go figure out where the object resides and create a TCP connection. Okay. In the second case, you are actually going to call an explicit bind call, which is called explicit binding. So you are going to say, I am going to call some methods on this object, okay, which is object ref, okay, and then say go find it and then give me a handle to it, and then you are going to do object pointer dot method. Okay, so in either of those two cases, when you do binding, you are going to go look up the name service and figure out where the server runs, okay, and then connect to the right socket. Okay, is that clear? You will have to do this in your lab as well, okay, because when you write your peer-to-peer code, peers will not run on the same machine. They'll run on arbitrary machines. Okay, you should typically not hard code anything like socket number. So you will have to register your peers with some naming service and have the peers look up one another and so on. Okay, so same, all of these concepts you will be applying in your lab. So you should understand what naming is and what binding is and so on. If you have some familiarity with RPCs, this is not hard. In any case, not hard, but you need to understand these things have to happen for the client and the server to talk to one another. Any questions here? Yes. Question.
Since RPCs can be done over the internet,
Yes.
right? So are there any port forwarding issues by ISPs which people face generally? Like what ports do these connect on?
Okay. The question is, since you can make RPC calls to any machine on the internet, are there issues of port forwarding and whatnot? Okay, so typically, so we have implicitly assumed that the client and the server are able to talk to one another, meaning that the server has an IP address that you can directly connect to. Okay? Now in some cases, if your server machine is behind a firewall or some such thing, then the firewall might block certain ports. In that case, it's up to whoever is running the server to make sure the firewall is able to forward packets that are destined for the server through the firewall. Okay? We have ignored all of those issues because they are separate network configuration problems. They are not related directly to RPC mechanism. Okay? In any case, if you have any client and any server, whether you use RPCs or not, if the server or the client is behind a firewall, then you have to ensure that the firewall will let the traffic through. Okay? So yes, indeed, if you have a firewall between these two, you have to ensure that the firewall is appropriately configured for this communication to take. And that's independent of RPCs. This could just be a browser connecting to a web server. You still have the same problem.
Are there any standardized ports or any range of ports for RMIs in Java?
Okay. So the other question is, are there standardized ports for RMIs? So there is no standardized port. All that you are doing is you can listen on any port. You register that port with a naming service. Okay, the naming service listens onto a regular port, so the client can go look up where the server is listening. Okay. So this is basically because you can have any number of these servers on that machine. So you cannot standardize a port saying RPCs can be only on these ports, because you can have 20 servers, they're all supporting RPCs listening for RPC calls. So there is nothing standardized in terms of port numbers. Other question here? Okay. So the one more difference between, important difference rather, between RPCs and RMIs is in RPCs, the parameters were passed by value, not by reference. Okay. RMIs will relax that assumption for us, okay, and we'll see how. But let me ask why RPCs restrict passing parameters by value rather than reference.
Since they have different address space.
Okay, they have different address spaces. What does that do?
You cannot refer another address space memory from another process, right? That's the reason you cannot access the same object.
Okay, so passing by reference essentially means passing pointers. Okay, pointers are memory addresses. Okay, that when you have a memory address, it's specific to a machine. You're saying memory address X on a particular machine. If you pass parameters by reference, and then those parameters are sent to a second machine, if you try to dereference that pointer, okay, it's going to look up the address X on that machine, not on the sending machine, so that address doesn't make any sense at all. Okay? So you cannot, as a result, pass by reference, because when you dereference a pointer on a second machine, that address is garbage because it's actually referring to a memory address on the sending machine. So it doesn't make sense in most cases to do this, which is why you pass by value. Pass by value essentially means you make a copy of whatever the parameter you're passing and send the copy over. Then you basically just look at the copy. Okay. Now in RMIs, you can actually pass by reference. You can essentially send object references from one machine to another. Okay. Now, in this case also object references will refer to memory addresses in the end. Okay. So essentially this is going to generalize the notion of a memory pointer into a network pointer. Okay. So you can dereference a network pointer because it will tell you, go look up this address on this machine, rather than saying just here's an address. Typically a memory address is just an address. Okay, so passing by reference in RMIs requires you to generalize the notion of a reference, so you can dereference it over a network. Typically you dereference locally, so you just say I go and look up a certain address. That won't work if you are passing object references. Okay. So RMIs actually have generalized this notion, so you can actually pass by reference in addition to passing by value. And specifically in the Java case, you can essentially take a method and you can pass an object as an argument to the method. Okay. So that object typically would go as a reference. Yeah, in Java what happens is if it's a local object, you are going to actually send a copy of the entire object. If it's a remote object, you are going to send a reference. Okay. And this is an example with 3 machines, okay, A, B and C. Okay. So this is the client machine. A is the client machine, C is the server machine. Okay, so you are essentially making a call, RMI call from A to B. Okay, except that in that call you are going to pass 2 arguments, O1 and O2. Okay, so I'm going to show you what is actually being called. So let's say you call a remote method and you pass 2 arguments O1 and O2. Okay, O1 is a local object. As you can see, the O1 is right here. Okay. O2 is actually a remote object. Okay, O2 itself resides on a 3rd machine altogether. So what happens in this case, in Java's convention is, if you're passing a local object as an argument to a method, it's going to be passed by value. So you will make a copy of O1 and send it over, so you get a copy of O1 here. Okay, so then any subsequent calls on O1 will actually be called on the local copy here, not on this one. But if you have a remote object that you're passing as an argument, that is passed by reference. Okay, that is going to be passed as a network pointer. So when machine C calls a method on O2, it actually goes back to the original object. Okay, is that clear, what I just said? Okay, because this is being passed by reference. If you call O2 dot some method, it will actually become an RMI call on O2. Okay? But if you call O1 dot method, because O1 was passed as an argument here, if you call some method on O1, it will be called on a local copy of O1. Okay, so that's Java's convention. You could argue why its local objects are passed by values, remote object by reference. That's a separate discussion. Okay, that's how Java programmers, or rather Java designers, decided to implement object. Okay, but the more important part is you are able to pass by reference. Okay? O2 was actually passed as a reference, not by value, which relaxes an important restriction that RPCs imposed, which is you can never pass arguments by reference. Okay? In RMIs, that is actually allowed. Okay? Not all RMI systems, at least some RMI systems allow it. Okay, yes, question.
Does O1 need to be immutable, or can Java RMIs support mutable objects?
The question is, does O1 need to be immutable, or can it support modifications? Is that what you're asking? So what will happen in this case is you can start making calls on O1 which might modify local state. That state will not change O1, the original O1. So you will basically have a copy that's being changed. This is exactly how you pass by value. When you pass by value, if you change the parameter inside the called function, it doesn't change the original parameter. The same would be true in this case. Okay? There's a question in the back.
Yes. So will there be any, due to the network overhead, will there be any significant increase in runtime?
Okay. Question is, due to network overhead, will there be significant increase in runtime? So as you can imagine, object O1 could be an arbitrary object. It can have any number of parameters as part of its private or public variables. It can have any number of methods on it. All of that has to be packaged and sent over. Okay? So if the object O1 is large, there is going to be some significant overhead in actually sending that as part of the RMI request. Okay? So yes, if you start passing entire objects as opposed to simple parameters like variables, the overhead for RMIs will go up, because you have to actually pass the copy of the whole object, and the entire state has to be copied over.
What about the other, when you are doing, you are passing by reference, for every time you want to access memory location, essentially making an RMI call. So that will very significantly increase the runtime, right?
Okay. So the question is, if you are passing an object by reference and then you start invoking methods on those on that object, then it becomes an RMI call. And then RMI calls will have high overhead. So that's also true. RMI calls will always, any remote call will always have higher overhead than a local call, because to call that remote method, you have to construct a message and send it over a network. In a local method, you're simply calling a function, okay, or a method locally. So all RMI requests will have significantly higher overhead. Okay, so this is not a performance argument. This is basically in a distributed system, you have to pay the price of communication and the overhead that comes with it. What you are getting is the ability to take your application, partition it across multiple machines, and still call methods that are local to each process. Okay, so you get that benefit, but the overhead of making RMI calls is not going to be small. Okay, yes, question.
Suppose there are getter methods in the remote object which is referenced, passed by reference. So does that getter, so is the object's parameters also passed internally, the private parameters? So the private class variables, are they also passed, or is the getter making a synchronous RMI call and then waiting for a response?
So you are asking if you pass an object by value.
By reference. Suppose you
If you pass an object by reference, then all you're passing is a pointer to the object. You're not passing anything with the call. Every method is actually going to be sent to the local, to a remote object, and if you want to say get a certain variable, it will look up that variable and send back the result. Okay? If you are passing an object by value, you make an entire copy. In this case, you will actually look up the copy of those variables. If this the state has, O1 has changed on the sending machine, you are not going to, if you start making object calls concurrently on that. Yes, question there.
In addition to that, if it is an asynchronous call and it's remote, if it's passed by reference, will there be any race conditions?
Okay, question is if you have an asynchronous call and you have, will there be race conditions for asynchronous calls on remote method? So what you have to realize is whether it's synchronous calls or asynchronous calls. Okay, if you are going to have multiple machines making calls on an object, you better have synchronization built in. That is the same as you have two threads within one process that are calling methods of the same object. If you don't have synchronization, these threads will trample on one another. Here you might have two processes, not two threads that are making a call on a certain object. If you don't use synchronization, then you are going to have problems. That is independent of whether it's a synchronous or asynchronous. Concurrency always requires synchronization. Okay? How you call is not material in that case. Okay, so before I will come back to synchronization in just one slide, but let me show you an example of remote or distributed objects that is used in a middleware system called DCE. Okay, this is an old middleware system, it doesn't exist anymore, it's outdated and nobody uses it now, but this was something that was used 2 decades ago. But what is interesting here is there are two kinds of remote object invocations. Okay, so here is what is called a dynamic object and that is called a shared object. So typically what we have seen in the previous slide in the Java case is when you call a remote object dot method, essentially all of those calls are actually calling the same object and the method on the same object. So if this client 1 makes a call and it modified some local variables or private variables in there, then client 2 makes a call, it will actually see those modifications because it's the same object. You are calling multiple methods on that object. So when one method modifies the state of the object, that state becomes visible to other methods, other method calls. Here is a different scenario where every call of a remote call actually instantiate a new object first. Okay. Then you execute the call and then that object is destroyed. So you essentially have a class. When a call comes in, you will instantiate a new object of that class, which is essentially called a private object. And that private object is specific to just that call. You will execute the method and then you will destroy that object. So in this case, state is local to that object and it is ephemeral. It goes away once the object is destroyed. In this case, the second case, the state is shared. There's only one object. Now you might ask, why would you actually want to create an object every time an RPC or an RMI request comes in? Okay. This is very similar to a thread request per thread model or a thread per request model rather. Okay. So if you have a server listening on to for some request, when a new request comes in, you can start a new thread. The thread can process that request and then the thread dies after it's done. Okay. That is essentially what's happening here. When a client request comes in, you start a thread, you associate an object to process the request. That is, you could think of that as an HTTP processing object. So if an HTTP request comes in, it will process the HTTP request, and once the request is done, the thread will be terminated and the object will disappear. So you can use this in cases where there is no shared state across requests. Each request is independent of one another. They're simply processing independent requests. Okay, so DCE supports both kinds of remote objects. One where these are more stateless in nature. There is no state shared across different invocations of the same object. In the second case, there is shared state. So there's actually only one object that is shared by all the calls.
You could still shape the state using class variables right over there.
So the question is, can you still share state using class variables? So since you have made multiple instantiations of the same object, so you will have object 1, object 2, object 3 that all derive from the same class. If some variable is changed in object 1, it won't be reflected in object 2 because that's an independent object.
Yeah, but I'm talking about the class variables, static variables.
Yes, you could have global variables that are separate from this. Indeed, you can have state that is independent of this object that could be modified. That's a different problem. So in this case, what is part of the object is not going to be shared state. That's all I was saying. You can have shared state outside the object. Okay, so that's just an example of how some systems implement distributed objects. But now I'm going to talk a little bit about Java RMIs, and then we will look up some other concepts in RMI. So in the case of Java, so good news about Java is it supports RMI as part of its language runtime. Okay, so it's built into Java's features. You can easily take a class and make it a remote object, okay, by just saying that it inherits from a remote object. Any class can be made into a remote object. In that case, the public methods of the class essentially become remote methods that can be invoked by other processes sitting on other machines. Okay, so when you write code for servers in Java, you have to define the interface and the implementation. The interface is essentially then registered with the remote object registry. This is the naming service in Java. Okay, so there is a remote object registry. So when the server starts up, you will register that server with the remote object registry. So then clients can look it up, saying where is the server running and so on. Okay, so the client, when it starts up, is the stop code of the client will look up the server in the remote object registry, and then from that point on, you are going to use normal call syntax. Okay, so you are simply going to say object.foo. Okay, the same syntax that you use for any local object method invocation, you are going to use for remote object method invocation as well. Okay, so note that when you do this, you are not specified where the server is running, the IP address of the server, port number. You are simply calling methods on objects like you normally do. Okay, it just so happens that these are not local objects, they just sit on some other machine. Okay, but your stop code will take care of figuring out where the object resides, how to call the method, and so on. Okay, so from programmer's perspective, it vastly simplifies coding because you are not writing lower level network code. Okay, all that is done for you by the stop code. Okay, so you are simply going to write your application as if you are calling methods on any Java object. It just so happens that these are remote objects. And two tools that you are going to use if you are going to use Java code and write RMI is RMI registry is the server side name server where you register yourself. And then just as last time you saw RPC gen as a RPC compiler, in Java you essentially have RMIC, which is the code which will use the interface definition to, it's an ideal compiler. So you're going to use your interface definition to create stub code that you will then include as part of your Java code. Okay, so these are tools that you will need to use if you're going to write your lab in Java, for example. Okay. Any RPC system will have these kind of tools that will create stub code for you and whatnot, so that you don't have to write all of that code. Any questions on this? Does anyone use these tools? So you will, if you haven't, you will use it as part of your lab. Okay, whatever language you have doesn't matter. You will basically use some variant of these tools. Okay. Okay. So the last part here is synchronization, which there was a question about synchronization earlier, and I said I would come back to it. So the part that you will have to keep in mind is if you have multiple methods that are being invoked on an object concurrently, you will have to implement synchronization. Just as if you had multi-threaded Java code and you had multiple threads calling methods of an object, you had to actually synchronize calls to that object. And that is going by using any synchronization primitive that's supported in Java. And now, if you have used synchronization in Java, you will know that it is very easy to implement synchronization. There's one keyword called synchronize. Okay, if you essentially take any method, okay, if you have any public method, if you stick the keyword synchronize in front of it, Java will automatically implement a lock for that object. Okay? And then all method calls will become synchronized. Okay? So essentially, if you're writing a class, and then you have, let's say, void method foo. Okay, let's say this is public. So if you then, instead of this, if you say void synchronized foo, that essentially makes this object into what's called a monitor. It implements a lock for this object. So now if multiple threads start calling foo, automatically you will have mutual exclusion. Only one thread will be allowed to execute foo or any other synchronized method of this class at any given time. Okay. This is how Java supports synchronization. And I'm assuming that if you're taken an undergrad class in OS, you know these kinds of synchronization primitives. Okay. So now the question is, how do you extend this for a distributed environment? Okay. This is done in Java for a single process with multiple threads in it. And now in our case, in RMI, you have multiple processes that are calling methods on remote objects. So you have to extend this notion to how you can actually do this over a network. Okay. Now, this essentially requires you to take the concept of a lock, which is what synchronized keyword implements internally, and make it a distributed lock, okay, which is a non-trivial problem. We'll look at how to implement a distributed lock in the next chapter, okay, or actually 2 chapters from now. Okay, but for the purposes of what you need to know now, okay, you do need to implement some synchronization. Okay. Synchronization can be implemented either at the client side or the server side. Okay. Now, if you implement it at the server side, what is going to happen is remote method calls will come in, okay, and then the stub code at the server will actually allow synchronized access to the methods. So they will say if one call is executing in that method, other calls will have to block, okay, and then so will the client process that is waiting for the results. Okay, so this is essentially block at the server method. You can also block at the client end. The client may not even, the client stub code may not even send the request if you know that the method is actually already being executed at the server. So you are going to block, so you'll actually block at the client end and only send your request at the later time. Okay, so you have both options available to implement distributed locking. In one case, the locking is done at the server side. In the other case, each client coordinates and says, I will not even send my RMI request. The client stub code will say, I will not even send my RMI request if the server is busy, the lock is already in use. Okay, so these are all important issues to know. Okay, now, you don't have to actually go implement distributed locks for the lab, but I do want you to know that synchronization becomes a more thorny problem when you have remote objects. Because what was fairly straightforward to implement using the synchronized keyword, which is built-in keyword in Java, okay, for a single process application, becomes a lot more complicated when you have distributed application, because your locking has to be coordinated by a set of processes. Okay? And then all sorts of things can go wrong. A client process holding a lock may crash. Okay? If a client process holding a lock has crashed, then all other clients are permanently blocked because that lock will never be released. Right? So these are all problems that you will see in a distributed lock, because your set of processes, if some process crashes while holding the lock, then everything else will block and you will essentially end up in a deadlock. Okay, so a lot of these issues have to be dealt with. Okay? We will come back to these issues when we do distributed locking and distributed mutual exclusion. Okay, as I said, in 2 chapters from now. But something you have to realize has to be done when you have synchronization. Because if you have multiple threads or multiple processes calling methods on an object, you have to synchronize those requests. And then how to do that in a distributed environment is a non-trivial issue. Any questions on this? Yes?
Where does security fit into the RMI world, the RPC world?
Okay, that's a good question. The question is, where does security fit into the RMI world? Now, that's a very good question, because what you have to realize is when you send an RPC request or an RMI request, it is going unencrypted over the network. That means any arguments that you are passing are also going in clear text. If any intruder actually intercepts your network packets and looks into the contents of those packets, all the arguments will be revealed. So for example, if you have username and password being passed as your arguments and you're making an RPC call, all of that is going unencrypted. Okay, so what we have not talked about here is how you can use a secure version of RPCs or secure versions of RMI, which will encrypt all of your RPC code. That is also done by the stub code. I did not come to that here when we are going to talk about security very late in the course, I was going to come back to that, but since the question was asked, let me say what needs to be done. So if you want to secure your communication, you want to ensure that RPC calls or the parameters of RPC calls are not sent in clear text, you want to then establish encrypted connections between the client and the server, not regular TCP connection. Regular TCP connection don't encrypt any of the data, so the data is susceptible to intruders actually hacking and taking a look at your packets and so on. Okay? Now that can be done using any number of mechanisms. So you can, the standard thing to do is, rather than using traditional sockets, you use SSL, secure sockets layer. If you essentially run your RPC runtime on SSL, it will automatically create encrypted connections rather than clear text connections. That's a very straightforward approach that is available to many RPC systems. So if you are making any RPC calls over the internet, you better ensure that all your calls are actually, RPC calls are encrypted. Otherwise, the problem that I just mentioned will be there, where all the arguments are going in clear text. So the argument have any sensitive information that's going to be vulnerable to hacking. Okay, so the standard approach, to answer your question, is to essentially encrypt the communication. And one standard way to do this is to replace sockets with secure sockets, which will automatically create an encrypted channel for you. Okay? Any other questions? But security is something that's important as well, okay, although I have not mentioned that here. Whenever you have any distributed applications, ensuring security is important. So is authentication. Right? If you have a server listening on to for RPC calls, how do you make sure that only authorized users are making calls as opposed to arbitrary users? So for that, you will have to ensure authentication, where you can only allow authorized clients to access, not an arbitrary client to make a request and get some data from the server. Okay, so all of those are issues we will come back and look at when we do distributed security.
As well as data
Integrity, authentication, encryption, they're all security principles. We'll come back to that later. Yes, but integrity is as important as well. Any other questions here? No. So in that case, I'm going to move on to the next part of the lecture, which is to talk about lower level network programming, okay, using sockets, and then we'll look at MPI. So what we have done so far for distributed communications is two methods, RPCs and RMIs. Okay? They allow you to program at a higher level of abstraction. Okay? Application programmers don't need to deal with lower level networking issues. But if you so want to, can actually program directly at the socket layer. This allows you to actually have full control over how the client and the server, or how two peers communicate with one another. Okay, and here is the standard process that you will use to actually implement low-level socket communication. Okay, so the top part of the figure shows the code in the server, and the bottom part of the figure shows you the code that the client executes. In both cases, what you will have to do is to actually first create a socket. Okay? A socket is essentially a network abstraction that allows you to send and receive messages. Okay, so once you create a socket, on the server side, you are going to bind that socket saying, listen on this port. Okay, so if you have a HTTP server, you create a socket, you will actually listen on port 80. That is where all the messages will come. But if you're writing an arbitrary application, you will have to pick some unused port on that machine and bind your socket to that port. Okay? And this, you have to actually write code and figure out the port number and say, I'm going to now listen on to this port by binding. And then you call the invoke the listen call, which will say now the socket is actually listening for connections. It's waiting for clients to send it connections. Okay, and then you will basically sit in a loop from this point on. You are going to be sitting in a while loop, waiting to actually, so you call accept, which will say wait, block until some client makes a connection. Okay, so this is the part that the server has to do before anything can actually happen, any communication can take place. You create a socket, you bind it to a port that the server will listen on. You say listen, which will say the socket is ready for listening for network connections, and then you sit in a loop, try accepting new requests. Okay? On the client side, you will just create a socket and then you will connect to that port number using the connect call. Okay, whatever port you are bound to, you are going to actually specify that in the connect. And then you will essentially create a connection. This is the part where the client and the server will create a TCP/IP or a UDP connection. This is actually TCP/IP. So you will create a TCP/IP connection. Okay. So once this has happened, then you essentially use read and write calls or send and receive calls. They're equivalent in the socket word to actually send data and receive this, data back from the server. So if you want to send something to the server, you are going to write to a socket. If you want to receive something from the server, you're going to read from a socket. So you'll basically write and send data and the server will read, server will process it and write results back. So this will continue for some point until the communication is complete, at which point you will essentially close the connection. Okay. So this is all the code you will write as an application programmer. This is socket code. This is shown in a picture, but if you are interested, I can also give you some sample code so you can understand all the stuff application programmers have to write in order to program at a socket level. Okay? Lot more code has to be written. In the RPC case, all this was automatic for you. All of this code was still present, but it was part of the stub code that was auto-generated for you. So you did not have to write anything. Okay, so all of that is still happening under the hoods, but programmers don't write it. But if you choose to program at this level, you have to write all of this. And this is a template of how you are going to write a client and a server, or how you can have two peers communicate. Okay? So this is basically programming using what's called Berkeley sockets. Okay, and the reason I'm presenting this is we will now see how some other runtimes actually extend some of the concepts that vanilla sockets provide. Okay, but before I do that, let me see if there are any questions here. Is anyone programmed using sockets? Okay, so several of you have, which is good. So you at least understand what this means, and I'm going to now build on it and extend some of these ideas. Okay, so these are just listings of what the calls I just showed you, so I'm not going to go through that. Okay, so now let's take what is called Berkeley sockets and extend it to other mechanisms that will provide us a richer interface. Okay. So traditional TCP/IP sockets provide a simple send receive primitives or read write primitives, and moreover they are blocking primitives. Yes, both send and receive or read or write are blocking calls. Okay, they will essentially block waiting for the data to be sent to. Now what if you wanted to program sockets using asynchronous calls? How would you do that? Okay, so now for that you have to use other runtimes. So Berkeley sockets do not provide you that abstraction. So one runtime we are going to look at is what is called Message Passing Interface, or MPI. So MPI is used for high performance parallel application. It's a special runtime that was developed for very high performance applications written, for example, for supercomputing simulations and so on, where even the overhead of TCP/IP processing was too high. So if you wanted direct access to the network interface and wanted to program really at a low level, and you wanted complete control over how messages are sent, what overheads are seen by messages, whether you will be blocking or non-blocking, then you have to implement your application using MPI. It uses a socket-like interface, but it gives you a lot more flexibility than traditional sockets. And I'm going to show you some examples. So the thing to keep in mind is MPI is used for parallel applications. Okay? It is used for parallel programming environments. So if you've done any parallel programming, you will see that MPI is still a popular runtime of choice. Okay? You will actually program to an MPI interface, not using you will not use an RPC interface or a socket interface. You will use an MPI interface. And I'm going to show you some primitives that MPI actually provides. The thing to keep in mind is in vanilla sockets, there is one send and one receive. Okay? In this case, you will see that there are many different flavors of send. In fact, there are 6 different flavors of send, and there are 2 flavors of receive. Okay? And they differ in what the send actually does. Okay? And you will see that so there is a B send and a send and an S send, a send receive, and so on. Okay? So essentially what B send does is it will append the message to a local send buffer and return. So it's a non-blocking version of send. Okay, all you have done is you have a send and you have some data, that you're given to the send call. And it'll just copy it into some local buffer and it'll return, and it will be asynchronously sent to by the OS or the runtime at a later time. Our send is a traditional blocking send. This is exactly what normal sockets would do as well. You'll send a message and you'll wait until it's copied to either local or remote buffer. Typically, when you do TCP/IP send, when the send returns, you essentially know that the send has actually succeeded. So TCP/IP will block, it will make sure acknowledgements come back and so on before the send returns. Okay, so it's somewhat of a blocking version. And so that's the same thing what MPI send does. Okay. S send will actually extend that further. It will say you send a message and you will block until the other end has actually taken delivery of the message. Not even that it has reached the other machine, but the process at the other end has actually started receiving the message. Okay. So this tells you not only did your message, so this previous call tells you that the message reached the other machine. This next call says not only did it reach the other machine, it actually reached the application. The application has actually taken delivery of the message. Okay? So if you want to ensure that the application has actually received the message, you will use send. And then there's another variant called send receive, which says send a message and wait for a reply. So you'll say make sure the message was received at the other machine, make sure that the other application has received the message, and then wait for it to actually construct a reply and send it back to you. Okay, what does this remind you of? Okay, so this is RPCs. Okay, that's what RPC does. You send a request, you block all the way until a reply comes back. So RPCs are implemented in a trivial way. It's not real RPCs, but it's the same abstraction as an RPC, is where you use MPI send receive. You say send a message, make sure it's received, make sure it's delivered to the application, let the application process it and wait for a reply to come back. Yes, if you want to do all of that, you will use the send receive call. And then you have another one called iSend, which says here is a pointer, okay, that has some data, just send it. Okay, I'm not even going to wait for it to be copied to the OS or be sent or anything like that. So this is the least blocking of all. You just put the message into a buffer, you hand the pointer to that buffer to the OS and say go ahead and send it out. I'm not going to wait even for the send to take place. Okay, so in some sense this is the least blocking of all. Okay, and then you have B send, send, S send, and send receive that are increasingly blocking, and you basically get more and more information as to what is actually happening. So you can pick from any of these flavors in MPI depending on what you want to achieve with your application and what performance overhead you are willing to tolerate. Okay, so you can see this nicely generalizes what plain vanilla sockets give us. Okay, you can actually use different variants to do this. Okay, at the other end, you have two variants of receive. There's a blocking receive, which says when you call receive, you just block until some message arrives over the socket, an MPI socket. Okay, and then there is a non-blocking receive, which is I receive, which says check if there is an incoming message, but if there is no incoming message, don't block, just return saying there's no message pending. Okay, so you can basically this is more like polling, saying if there is a message, pick it from the queue and return it. If not, just return saying there is nothing waiting. Okay, so you can have a blocking as well as a non-blocking version of receive. Okay, so this should give you some notion of how you can take a traditional socket implementation and generalize it to get various different flavors. Okay, and so again, you have synchronous, asynchronous, and various variants that MPI will give. Any questions here? Okay, so if there are no questions, I will stop here today. We will, as I mentioned, for those of you who came late, there is going to be a class on Wednesday, that's a regular lecture. But there will also be a class on Friday, which is the makeup class that I missed 2 weeks ago. Okay, so make sure that you come not only on Wednesday, but also on Friday for the makeup class.